Greetings, welcome to this new video about Thevenin's theorem. In this video I will demonstrate the application of the Thevenin's theorem through a step-by-step example explanation. By following along carefully, you will gain a clear understanding of how to apply Thevenin's theorem to solve practical problems. Let's dive in and begin with the solve the problem number 5. Let's consider this network consisting of 3 resistors labeled R1 through R3 as well as 3 independent sources. The question now is to find the Thevenin's equivalent with respect to terminals A and B. Let's move on to the solution. By applying the Thevenin theorem between terminals A and B, we can replace this circuit with a voltage source in series with a resistor, which will be denoted as VTH and RTH. I will start first with the determination of the Thevenin's resistance. This step can be done by removing all independent sources in the circuits, which means the voltage source will be replaced by a short circuit and the current sources will be replaced by an open circuit. The Thevenin resistance represents the equivalent resistance between terminals A and B. That means RTH is equal to the series combination of R1 and R2 connected in parallel with R3. Therefore, RTH can be calculated using this formula: R3 times R1 plus R2 over R1 plus R2 plus R3. And if we replace the resistors with their numerical values, we obtain RTH is equal to 4 ohms. After finishing the determination of the Thevenin resistance, we proceed to calculate the Thevenin voltage. The Thevenin voltage is basically the open circuit voltage calculated between terminals A and B. To find the open circuit voltage VOC, I will apply Kirchhoff's laws. And I will consider I1 is the current through the resistor R1, and I2 is the current through the resistor R2, and I3 is the current through the resistor R3. By applying Kirchhoff's current law at node 1, we can write IA minus I1 minus I2 is equal to 0. And if we replace IA with its numerical value, we obtain 1 minus I1 minus I2 is equal to 0. Now, by applying Kirchhoff's current law at node 2, we can write I2 minus IB minus I3 is equal to 0. And if we replace IB with its numerical value, we obtain I2 minus 3 minus I3 is equal to 0. Now, by applying Kirchhoff's voltage law at loop 1, this is loop 1, we can write negative R1 times I1 minus Vs plus R2 times I2 plus R3 times I3 is equal to 0. And if we replace the resistors and the voltage with their numerical values, we obtain negative 6 times I1 minus 14 plus 14 times I2 plus 5 times I3 is equal to 0. From equation 1, we can write I1 in terms of I2. That means I1 is equal to 1 minus I2. And from equation 2, we can write I3 in terms of I2. That means I3 is equal to I2 minus I3. And now by substituting A and B in 3, we derive one equation in terms of I2. And if we continue simplifying this equation, we obtain 25 times I2 minus 35 is equal to 0. That means I2 is equal to 35 over 25 is equal to 1.4 amps. And from equation B, we have I3 is equal to I2 minus 3, and if we replace I2 with its numerical value, we obtain I3 is equal to negative 1.6 amps. And according to Ohm's law, VOC is equal to R3 times I3. And if we replace R3 and I3 with their numerical values, we obtain VOC is equal to negative 8 volt. That means VTH is equal to negative 8 volt. The Thevenin equivalent with respect to terminals A and B is a negative 8 volt voltage source in series with the 4 ohm resistor. After completing the calculations, I perform a simulation using SPICE to verify our results. Now let's proceed to the SPICE environment. Here is our network drawn in SPICE simulator. This is resistor R1, R2, R3, and the independent sources current source IA and IB, and the independent voltage source VS. And I connect here a load for both the original circuit and the Thevenin equivalent circuit. Now I need to simulate their behavior. I will go to Analysis, DC Analysis, Calculate Nodal Voltage. We can see here that the voltage across the load resistor is equal to negative 1.6 volt in the original circuit and is equal to negative 1.6 volt in the equivalent Thevenin circuit. Upon simulation, we can observe that the two circuits have identical behavior when we connect a load between terminals A and B. This outcome confirms the accuracy of our calculation. Alright, thank you for watching this video. If you have any question, do not hesitate to contact me by email or leave a comment under this video and I will answer you as soon as possible. If you like this video, don't forget to subscribe and share. Take care and see you next time in another video about Thevenin's theorem. Bye bye.